Good morning, everybody. I'm Volker Schamiris. I'm a lead scientist here at DESI Theory Group, and also the spokesperson of the Wolfgang Pauli Center that Beate Heinemann mentioned in her introductory comments yesterday. And I want to welcome you all on behalf of my colleagues, mathematical physics colleagues here at DESI at Hamburg University, and also on behalf of the Wolfgang Pauli Center. Now, this welcome also extends to those of you who are online present. I think we have about 50 people that decided to follow this course online. So some of you maybe did not quite know what to expect. I think from this week, I think after yesterday's wonderful kickoff talk, you all know what you're in for in the next 3 days. So we hope that you all followed our advice to read the lecture notes and come here well prepared. Now, nevertheless, there could be still questions. You're welcome to ask questions during the seminar, during the talk. In that case, if it's possible, just talk straight into a microphone. So we would hand you the microphone and we don't have to repeat, although Edward was perfect in remembering to repeat questions yesterday, but we can do that step. So for people that are remote connected, it's a webinar, so you won't be able to ask questions directly, but you can put questions in the chat, and there will be people here sitting to kind of forward these questions either during the talk or at the end of the presentation. Now, so beyond that, maybe one more thing. I mean, so for the lecture for Edward, of course, this is a very tough program. At least I should say maybe. So I have given 2 talks a day on various occasions on several days in a row, and I felt it was a very tough load. For you, it's probably a little more relaxed program. You have a bit of time to kind of go read the lectures. And also we designed, you may have seen the cookies and the coffee, we designed these time before the lecture and after the afternoon lecture so that you can hang around, maybe talk to your peers or some other people to just discuss a little bit more, let things sink in. And make good use of the next 3 days. It's going to be, there's a question already. The lecture notes on the pad, but I think the lecture notes are available, as you know, and there will also be recordings available at some point. I think if you push, you might be in a position to push strong enough to have that released, but this needs to be discussed. So far there is no plan to release and no signatures that we are allowed to release any of that. Anyway, so without further ado, let's get back into black holes and welcome Edward Witten again.
Thank you.
The stage is yours.
Okay. So I'm going to assume that you all either heard last night's lecture or else have been reading the lecture notes. So I'm not going to repeat the motivational part from yesterday, but I do want to briefly review the main derivation and to elaborate on some points. So remember we were discussing what you'd see far away from a black hole that formed by the collapse of a star. I'll try to draw the Penrose diagram. So future infinity is up here, and the late-time observer is over here. This diagonal line is the black hole horizon. So the late-time observer is in the far future and far away from the black hole, outside the horizon, but the way a Penrose diagram is constructed, that ends up being up here. And the late-time observer is collecting signals that are coming out from the black hole at a late time, which we idealize as signals escaping at the speed of light. And then we zoomed in on the important part of the picture. The important part of the picture is the part near this corner here. I'm just blowing it up. So the red lines are signals escaping from the black hole at the speed of light and being detected by this observer up here. And we imagine that they originated, well, causality in physics in general says that whatever you observe could have been considered to originate on any given initial value surface in the past. We just take a convenient one that's to the future of all this commotion where the star collapsed to the black hole. And then we introduce a coordinate u that measures how far you are from the horizon on that initial value surface. Exactly how u is defined isn't important. What's important is only that u is 0 at the horizon. U is positive outside. Its derivative is non-zero on the horizon. And then the late time observer just has short shield time, you might call it. So this black hole is asymptotically flat. So our late time observer is far away, and what that observer calls time is just ordinary Minkowski space-time, I could have called it, instead of short shield time. But then we needed to know the relation between the time of the distant observer and the distance from the horizon at which the signal originated. And yesterday I just wrote down the formula, and I'll do so again now, but in a couple of minutes I'll give you a derivation of that formula. So this is the key formula that leads to Hawking's effect. So a signal from behind the horizon will never emerge. So if u is negative, the observer will never detect the signal. As u goes to 0, the time at which the signal emerges gets later and later, but only logarithmically, as we'll compute in a little while. So we could invert that formula to learn that u was c times e to the minus t over 4gm. So this is the key formula, which we'll derive in a little bit. But I just want to briefly review how it leads to the Hawking effect, and then we'll go back and derive that formula. So the distant observer measures a quantum field which we might call psi. It depends on the time and also on angular variables. And it depends on the distance from the black hole as well, but the observer is at some fixed distance, so I'm not going to write that explicitly. But of course, psi of t and omega can be expanded in partial waves. So for a spin zero field, for example, the expansion is in ordinary spherical harmonics. And we're going to just talk about one spherical harmonic. Well, maybe I should include R, sorry. It would be better to write this formula including R. The observer will live at a particular R. But I want to emphasize that each partial wave becomes a 1 + 1 dimensional quantum field, depending on the radial distance and also time. And they're decoupled, so the observer, let's say, measures, well, let's just discuss one particular psi Lm. It's a 1 + 1 dimensional quantum field. To simplify notation, I'll just call it psi of R and T. And then we set R equal to R of the observer anyway. So yesterday it was psi of T with the position of the observer understood. What did I lose? But now you can see again, right? Okay. So, as I said yesterday, the observer measures correlations of this field. For example, if psi was a component of the electromagnetic field, then by measuring the two-point function of the electromagnetic field as a function of time separations, that would give you the frequency dependence of the outgoing electromagnetic radiation. But in real time, you would just measure a time-dependent correlation function. So a device that is measuring the frequency of electromagnetic radiation is basically measuring such a two-point function and Fourier transforming it. So, now, so let's first discuss what you would have near the horizon. Well, near the horizon, we'd have a two-point function in terms of the u-coordinate. And in about 15 or 20 minutes, we'll start discussing a more realistic model. But yesterday's model was a simplified model in which I assumed the 1 + 1 dimensional quantum field. I took it to be a free fermion, a free massless fermion. And I also took it to be chiral because we only care about the outgoing mode, which is going to reach the observer at infinity. Whatever's coming in isn't of interest. So we're only interested in the chiral outgoing part of this field. And something you might know is that in vacuum, the two-point function of a two-dimensional massless field just has a simple pole, 1 over u minus u prime. Any two-dimensional field typically will have a power law singularity at short distances, but in this case the power is 1. And when I write du prime to the 1/2 in the numerator, that's just a way of reminding me that psi has dimension 1/2 in the two-dimensional sense. So when I change coordinates, I need to not just replace u by a corresponding function of t that we had up here, this one. I also need to rescale by a factor that comes from the fact that psi has dimension 1/2. And to make that mechanical, I just put du prime to the 1/2 on the right-hand side. So then when I change variables, I use the fact that u to the 1/2 is dt to the 1/2 times du dt to the 1/2. And I compute du dt to the 1/2 from this nice formula here. And then I find that psi of t prime, is what gives Hawking's answer. So a simple change of coordinates from the vacuum answer near the horizon gives us this nice answer near infinity, and it's, because we assumed a fermion, it's anti-periodic, not periodic in imaginary time. And that corresponds to a temperature related to the anti-periodicity, the Hawking temperature. There's a pi here, I guess. So there are a couple of things to explain about this. So first, why was it correct to use near the horizon the vacuum formula for the two-point function? I think I explained that well yesterday, but I'll just repeat it. When the observer makes a measurement at late time, u is exponentially small, and u prime is exponentially small similarly, and therefore u minus u prime is exponentially small. So the distances near the horizon that are being probed are much smaller than the distances probed at the LHC. And in particular, at such short distances, in any state, the two-point function can be determined by what it is at short distances in the vacuum. So near the horizon, it was correct to use this vacuum formula. Now, for the same reason, the exponential dependence between u and t means that the mode that arises at infinity with some fixed frequency, the observer has a detector that measures at some frequency. Whatever that frequency is, the mode started near the horizon at an exponentially large frequency. How large depends on how late you wait. But if you're measuring for photons of 1 electron volt coming out of the black hole, and you wait a time t, then the energy of the mode when it was near the horizon was bigger than 1 electron volt by this ridiculous exponential factor that I now can't find, but here it is. So the inverse, so The mode has been redshifted by a factor e to the minus t over 4gm before it reached the outgoing observer. So depending on what t is, that tells us by how much it was redshifted. But if you don't think it was at a high enough frequency near the horizon, wait another millisecond in the case of a solar mass black hole, and then it will be. So, because for a solar mass black hole, 4gm is just 10 microseconds or something. So after waiting a millisecond, you get another factor of e to the 100. So the mode started at an enormous frequency beyond near the horizon. And naively, here I'm going to cheat a little bit, and we'll fix it shortly. But naively, a mode of such high frequency just propagates freely from the near horizon region to infinity. To the extent that it's correct that it propagates freely, that means that to go from the near horizon observation to infinity, we just make the change of variables from u to t, which is what we did, and that gave us the Hawking answer. Are there any questions on that derivation? Yes? Yes. Well, it was at fixed something. So,
Could you repeat the question?
Fundamentally, the field only depends on one variable. It depends on two variables, but it has an equation of motion. It's assumed here to be a chiral free field, so it propagates to the right at the speed of light. And it depends on one parameter. It's constant along these red lines. So it depends on one parameter that measures which red line you're on. So near horizon, I parameterize it by u, but for the distant observer who's at fixed r, I parameterize it by t. But it's that family of outgoing red lines that we're parameterizing. Any other questions? So this actually is a textbook formula for the thermal two-point function of a chiral free fermion at temperature T sub h. The most elementary textbook derivation would involve a Hamiltonian approach. So you take the trace of e to the minus beta h, and you'd have to divide by the partition function, and then you'd have psi of t prime. And after a Hamiltonian calculation, eventually you'd get this formula on the right-hand side. There's actually a more efficient way to do it. The more efficient way to do it is to first write an action for the chiral free fermion. So the chiral free fermion is described by this kind of action, where t is, let's say, the real part of z. So then to do a thermal correlation function, to do a thermal correlation function, we work on a cylinder where t runs from left to right, but the circumference is beta. So real time goes from left to right, but imaginary time goes around the circle. It has a period beta, and the reason for that is that, remember that real-time propagation is by e to the minus iht. But if we're computing a thermal correlator up to this normalization factor 1 over z, we're using e to the minus beta h. E to the minus beta h is like e to the minus iht with an imaginary value of t. So we're propagating the field, in imaginary time by beta, but then we want to calculate this two-point function, psi of t prime, on the cylinder. And to get this formula, you only need to know two facts. So, you see, from this representation, it's manifest that this expression is holomorphic in Z, where T is real Z, except for a simple pole the simple pole at T equals T prime is what I used here near the horizon. There's a simple pole in the two-point function for coincident points. If you use the fact that the correlator is holomorphic in Z, except for a simple pole at, well, okay. Let me write it for complex variables. Then I'd say a simple pole at Z equals Z prime. And it also vanishes if the real part of Z goes to plus or minus infinity. It's a function only of Z minus Z prime. And it's periodic, or, what did I just do? I'm not sure I know how to recover from that. Okay, I'll try talking without the pages for a little bit while some technical difficulties are achieved. What I was trying to say was that the function we were describing is periodic in Z under a shift in Z by I beta. It has a simple pole at Z equals Z prime, and it vanishes at infinity. Those conditions are enough to uniquely determine it. So while the, are we starting over with a new slide? It doesn't matter if we are, I'll just draw the picture again. So it doesn't matter. If it's a new journal, that's fine. Let's not worry about fixing it. What I was explaining was this. The thermal two-point function, first of all, is defined this way. It's the trace of the product of fields in a thermal ensemble. So that's the definition. And you may have seen a textbook derivation straight from this definition for this or some similar calculation, maybe in 3+1 dimensions, in a Hamiltonian approach. But there's also a path integral approach where you continue from T to a complex variable Z, where T is real Z. So then you compute more generally psi of Z prime. And you would compute by a path integral now in a cylinder where the imaginary direction has period I beta, and the real direction is the T direction. And just from the fact that there's a simple pole as 1 over Z minus Z prime near Z equals Z prime vanishes at infinity, and periodic or antiperiodic under Z goes to Z plus I beta. These properties are enough to uniquely determine, sorry, I need to know how to create a new page. Oh, here, okay, sorry. Okay, these properties are enough to uniquely determine the function, which is the one that's been slightly erased. But see, if you look at this function, you see that as a function of a complex variable T, it has a simple pole at T equals T prime, no other singularities, and it's antiperiodic with period I beta. So those properties uniquely determine it. So it is, in fact, the thermal correlation function for this field at the Hawking temperature. The reason I went through that derivation was I wanted to make sure it was clear to everybody that anti-periodicity in imaginary time corresponds to a thermal correlator, because that will keep coming up. The heuristic reason, though, as a reminder, is the following. A thermal density matrix is e to the minus beta h, whereas real-time propagation is by e to the minus iht. And there's an obvious analogy between the two with beta equals it, or t equals minus I beta. So a thermal ensemble is similar to propagation in imaginary time through e to the minus I beta. But to get a thermal ensemble, we take the trace of the density matrix. Well, we take the trace of the density matrix times some other operators, which here was psi of t prime. Taking the trace means that after propagation through an imaginary time minus I beta, we close the loop. So that gives us periodicity, or for fermions, anti-periodicity with that period. So most of you have probably encountered that before in some form, but I wanted to explain some version to try to make sure everyone was comfortable with the idea that anti-periodicity in imaginary time has to do with thermal behavior, because it will come up multiple times, and I won't give such a detailed explanation each time. Any other questions now? Okay. Now there was this key formula. Yes?
During this derivation, we're always assuming that the black hole is a static system, right? The
Yes.
temperature never decreases, never increases.
Mm-hmm.
Okay.
Well, okay. The underlying logic is that we consider a quantum field in a fixed spacetime, a fixed classical spacetime. So what is the classical spacetime? It's formed by the collapse of a star to a black hole. Eventually, the star settles down. In fact, the no-hair theorem tells you that eventually the black hole does settle down to a time-independent stationary state. And our late-time observer is making observations in the far future after the black hole has settled down. That's why we have a time-independent spacetime. We're working to lowest order in Newton's constant. We're ignoring loops with fluctuations in the metric. So we're doing quantum field theory in a fixed classical spacetime that amounts to working in the limit g going to 0. For g going to 0, we do quantum field theory in a fixed spacetime background. The spacetime was dynamical. The star collapsed to a black hole. There was possibly a supernova. All kinds of things happened, but nevertheless, in the far future, by the no-hair theorem, it settled down to a stationary state. And what we investigated was what the observer will see once it has settled down to that stationary state. Now, you could ask, well, why is the approximation of quantum field theory in a fixed spacetime good? Well, it's good for an astrophysical black hole because they're so big compared to any length scale at which quantum effects and gravity become important. That's the quick answer. So then we discovered the black hole will evaporate. As it evaporates, it gets smaller, and quantum effects of gravity become slightly more important. And eventually, they become quite important at some energy which we don't know precisely, or some mass for the black hole we don't know precisely. But we expect it to be very, very tiny compared to the mass of an astrophysical black hole. Perhaps as small as the Planck mass, 10 to the minus 5 grams, maybe bigger than that. But for the overwhelming history of an evaporating astrophysical black hole, we would expect these approximations to be good. Any more questions? Okay, well, I wanted to give a derivation of this formula because it was, as you saw, the key formula in the derivation. And, well, the definition of what you're supposed to do to get that formula is to solve the geodesic equation for an outgoing null geodesic to find the relation between u near the horizon and t at infinity. So I could now write down the equation for null geodesic, and we could do it that way. That would be the most natural definition. There is, however, another approach which is a sort of shortcut and tells us things that will be important later, and that is, so we could use the geodesic equation, but there's a sort of shortcut which is to introduce the Kruskal-Szekeres coordinates. I'm sort of curious how many of you have seen them before. My guess is more people than have studied black hole thermodynamics, but I don't really know. The reason I think so is that I learned about Kruskal-Szekeres coordinates as a graduate student, but I didn't seriously learn about black hole thermodynamics till a lot later. So I'm assuming that might be true for other people too, but I don't really know. So my guess is a lot of you are familiar with what I'm about to explain, but since we're going to need it, I will explain it now. So Kruskal and Sekeres discovered this wonderful coordinate system for a black hole, whose main purpose is to understand the geometry behind the horizon better. And we will use it for that possibly tomorrow. But today we're going to just use it as a shortcut to find the relation between u and t. So you literally just define these new functions of r and t. You just change coordinates from r and t to u and v. And then you find that the metric, the Schwarzschild metric, I'll just write the Schwarzschild metric in those coordinates. Where from these formulas you can express r. So, okay. So r is now, there isn't an explicit formula for r in terms of u and v, but r is given implicitly by this formula. So that's just an alternative form of the Schwarzschild solution in different coordinates, where r is a function of u and v defined by this. So now if we want to look at a null radial geodesic, that means null means it's light-like, but radial means it's going in or out at fixed angles. So that means that d omega squared will be 0 along this geodesic. And to make it null, means that we need du dv to be 0. So du is 0 or dv is 0 to get a null geodesic, a null radial geodesic. And if you think about it, but you'll see that du is 0 for an outgoing guy, and dv is 0 for an ingoing guy. That's because, see, u, up to this little factor, is a function of r minus t. V is mostly a function of r plus t. So that tells you the function of r minus t is outgoing and the function of r plus t is ingoing. So a null geodesic, so the null radial outgoing geodesic is du equals 0, or in other words, u equals constant. So by knowing the Kruskal-Sekeres coordinates, we didn't really have to write down the geodesic equation. And u equals constant describes the null outgoing geodesics. Now, if you look at the formula, you see that with the standard definition, u is negative when r is bigger than 2gm. And we wanted a coordinate little u that vanishes on the horizon and is positive outside. So we can take, in the previous derivation, we can take u equals minus capital U, and that's r over 2gm minus 1 to the 1/2 times what? Where is it? So times this. So times e to the r over 4gm times e to the minus t over 4gm. So in other words, what I used in the derivation was that u is a constant that depends on the position of the observer but not the time, times e to the minus t over 4gm. So we've got an answer of that kind where the constant was this thing. So that is a derivation of the fact that I used, but it's not the optimal way to write the formula because we imagined that it's simply an inelegant way to describe it. We imagined the observer as being far away, so this constant is exponentially big in the way I've explained it. A better idea is to introduce the retarded time, t minus r, and then to write the formula by saying that u is the square root of r over 2gm minus 1 times e to the minus the retarded time over 4gm. So the retarded time, of course, is a better variable to use in describing what the distant observer sees than the ordinary time. The ordinary time at which the signal arrives depends on where the observer was. And it's more natural, if you're really trying to understand what happens when the star collapsed to the black hole and started to evaporate, to describe the distant observer's measurements in terms of the retarded time. And that makes the formula nicer because then the constant is big, assuming r was large, but it's not exponentially big. So anyway, this is the formula. Okay, this fact that u is exponentially small when the retarded time is big, with this coefficient 1 over 4gm, that was the main point that we used in deriving the Hawking effect. So any questions here? I see one.
Are the U V coordinates null coordinates?
Are u and v null coordinates?
Yes.
Yes, they're usually called null coordinates because there's no du squared or dv squared term in the metric. They're null coordinates because if only u is changing, ds squared is 0. Similarly, if only v is changing. So that's the definition of null coordinates. Another way, equivalent way to say it is that a surface where u or v is constant is a null surface. It has a degenerate metric with a 0.
Sorry, just one question. Why does U correspond to an outgoing geodesic and V ingoing?
Well, there's this slowly varying non-exponential factor, but the basic idea, near infinity, u is a function of t minus r, and the other one's a function of t plus r. So an outgoing geodesic is one in which t minus r is constant, asymptotically. In flat space, this factor wouldn't be here. So asymptotically, an outgoing geodesic has constant t minus r, which tells you that u is constant on an outgoing geodesic. An incoming geodesic has constant t plus r, which tells you that v is constant on an incoming geodesic. Any other questions?
Yeah, so there was a question about the space-time being fixed, but then you mentioned that the black hole evaporates. So there's some notion of dynamics in this space-time, right? How do we incorporate that?
In the classical limit, the space-time is fixed. Then we discover a quantum correction where, in fact, there's a temperature, but the temperature was of order h bar. It's analogous to the fact that if you study the standard model, in the limit that the coupling comes at 0, the W boson is stable. And then you start with that limit and do perturbation theory, and you discover the W boson is unstable. So in the classical limit, the black hole was like a big stable particle. Then we computed and found that it has a decay rate of order h bar, similarly to a W boson whose decay rate is of order h bar. Any other questions? Okay. So now I'm going to make a critique of this derivation. Well, first, there's a case where it's correct. There's a case where this derivation is strictly correct. But that case is a little bit exotic. That's a magnetically charged black hole and the radiation consists of a massless charged electron. Well, a massless charged fermion. I called it an electron, but I should have just said a massless charged fermion. So if you have a charged fermion, massless charged fermion, interacting with a magnetic monopole. And here our black hole is assumed to be a magnetic monopole because it's magnetically charged. The partial wave of the smallest possible angular momentum is a massless chiral fermion in the 1 + 1 dimensional sense. And in that particular case, our derivation is actually correct. So in my lecture notes, you'll find a reference to a paper by Modesena who studied this case in some detail. Now, could the case happen in the real world? Well, almost. If magnetic monopoles exist, which most theorists believe they do, even though they're hard to find, then a black hole could be magnetically charged. And although we do not have massless charged fermions, the electron is awfully light. So if you have a black hole whose Schwarzschild radius is much less than the Compton wavelength of the electron, which can still be big enough compared to the Planck length so that our discussion makes sense, then it's a very, very good approximation. The electron radiation from such a black hole would be described precisely by the derivation I've given. But we have to admit that's an exotic case, and we want to be more realistic. Now, if we're more realistic, what's going to happen? There was a step in my derivation that was actually oversimplified. I said that there was an exponentially large blue shift from the horizon to infinity. So a signal at some fixed frequency that we observe at late times started at an extraordinarily high frequency near the horizon. And therefore, I suggested that the wave would propagate freely near the horizon. That's true, actually. It'll also propagate freely near infinity because near infinity we have Minkowski space. It turns out, though, if you're careful, we'll see in the derivation, there's an intermediate zone. So there are two different reasons for the propagation to be free. Near the horizon, the energy is exponentially big, and at infinity, the space-time is flat, nearly flat. But in between, there's an intermediate region where R is not 2 GM, but it's more like 3 GM, as you'll see, where neither approximation is good. And it's oversimplified to claim that the wave propagates freely from the horizon to infinity. It's oversimplified except in this exotic case of a massless fermion interacting with a magnetically charged black hole. So a realistic derivation is a bit more complicated. Yeah, there are a couple things I wanted to tell you, though, before we got to a realistic derivation. That's what comes of not looking at my notes. Okay, well, we'll go back to the realistic derivation in a little bit. But first, I'll tell you a few general things. So first of all, we found that we'll be more realistic in a bit. But first, some generalities. Some more easy generalities. So we computed the Hawking temperature. And the size of the black hole is the Schwarzschild radius, 2 GM. So the temperature, in terms of the Schwarzschild radius, is 1 over 4 pi Rs. So that means that a typical outgoing photon, a typical outgoing Hawking photon, has a wavelength of order 1 over the temperature, which is of order Rs. So the wavelength of a typical photon is comparable to the size of the black hole, up to a factor of order 1. That's no coincidence, because the only input in the calculation was the black hole geometry. So what answer could we have gotten except that the photon wavelength was the size of the black hole? There wasn't any dimensionless number that could have come in. Now, if you have a body of area A and temperature T, radiating thermally, its luminosity is of order A t to the 4th times constants of order 1. So the luminosity is, of course, the rate of change of the mass. So the rate of change of the mass is, the luminosity is minus the rate of change of the mass. So the rate of change of the mass is of order minus AT to the fourth, and that's minus RS squared times 1 over RS to the fourth, or minus 1 over RS squared. So dm dt is then up to constants of order 1 of order minus 1 over g squared m squared. So from that you find that the lifetime is the time in which the mass changes by a significant amount. So it's actually, so this isn't temperature. The lifetime of the black hole is of order dm dt. It's the mass divided by dm dt, which is the time it takes for the mass to change by a significant fraction. So that's g squared m cubed. So the lifetime of a black hole of mass m is proportional to m cubed. So as I said yesterday, for a solar mass black hole, that comes out to something like 10 to the 67 years when you put in numbers there. And the approximations we have made remain good as long as the size of the black hole RS is now a function of the time because the mass depends on the time, but as long as that's much bigger than the length at which gravity breaks down, these approximations are good. Now, we don't really know what's the length at which classical gravity breaks down. It might be the Planck length. It might be a Kaluza-Klein scale. It might be a string scale. But whatever it is, it's a subatomic scale, certainly less than the length scale probed at the LHC. So some length between 10 to the minus 17 centimeters and 10 to the minus 33 centimeters, and probably closer to the lower end of that, is the length at which this would break down. So for the great, great majority of the lifetime of an evaporating black hole, our Hawking's approximations, which we've been describing, are good. Now, very late in the day, they will break down, and God knows what happens there, but humans certainly don't in detail. We presume that eventually the evaporation ends and we're left with stable elementary particles. After all, what else can happen? I don't know how to calculate the spectrum of exactly what you remain with. Another important point, which I think I said yesterday, if you restore h bar in the formula, the Hawking temperature is really this, with a factor of h bar in the numerator. That's why Hawking is not contradicting classical physics. In Einstein's theory, the black hole never radiates, its temperature is 0. The quantum answer is that the temperature isn't 0, but it goes to 0 as h bar goes to 0, in agreement with classical physics. So Bekenstein, as I said yesterday, had proposed a formula for the entropy. Well, he didn't really know the constant 4, but except for the 4, he proposed this formula for the entropy, which was order 1 over h bar. And even without Hawking's calculation, someone might have been inspired to realize from the first law that that means that the temperature should be proportional to h bar to the plus 1, so that the black hole could interact with classical matter where the energy is independent of h bar. And if one had been inspired to realize that Bekenstein's formula suggested a temperature of order h bar, you might have taken that temperature seriously, realizing it didn't conflict with the classical picture. If you look at Bekenstein's paper, you'll see that he does write down the first law, and he does get an answer for the temperature, but he doesn't like it because he's convinced that a black hole has zero temperature because of Einstein's theory. So even as daring as he was in writing that paper, he didn't have the nerve to take this further step that with 20/20 hindsight you might have taken. Okay, but now we're going to go back to give a more realistic explanation. Remember, I explained that the derivation we gave was fine for a massless electron interacting with a magnetically charged black hole. But in general, things are a little bit more complicated. And I want to give a more realistic derivation. And in a more realistic derivation, we're going to get what are traditionally called gray body factors. A black hole won't quite radiate as a black body. It'll radiate as what's called a gray body. So the starting point is what I've told you. We have some quantum field that we're trying to measure. In the real world, it would probably be the electromagnetic field. We make a partial wave expansion, and we treat each mode as a 1 + 1 dimensional quantum field. Now, I'm going to do it for a massless scalar field, just because the partial wave expansion is more elementary. If we were to do it for the electromagnetic field or the gravitational field, we'd have to use vector or tensor spherical harmonics, which are technically more complicated, and the greater complication wouldn't help us in understanding the ideas very much. So I'll assume a massless scalar, but the ideas are the same if we were doing electromagnetism or gravity. It's just the technicality of the partial wave expansion would be bigger. Another fact I should mention is that when I say we can reduce to 1 + 1 dimensional quantum fields by making a partial wave expansion, as stated, that's true for a black hole without angular momentum, a spherically symmetric black hole. You could ask me, what about a spinning black hole, a Kerr black hole with angular momentum that's not spherically symmetric? There's actually a miracle, which is that the standard wave equations in the field of a Kerr black hole are integrable. They can be solved by separation of variables in the right coordinates. So they do have a generalized partial wave expansion that leads to the same kind of story. I think it's a bit of a mystery why that's true. I've never heard of anything close to a conceptual explanation of it. It has been found empirically. But it means that a Kerr black hole can be treated exactly the way I'm telling you for a Schwarzschild black hole. A little bit more technicality, but the ideas are the same. Anyway, I have a massless scalar field that I'll call phi, and then we look at a mode of angular momentum little l. And so the action of phi is the usual free field action. But now we go to Schwarzschild coordinates, so I'll write I'll use the usual Schwarzschild coordinate system in writing these formulas. And then we, let's call this field capital phi. So I'll write phi in terms of partial modes phi Lm, where the PLM are Legendre polynomials. But by rotational symmetry, M doesn't matter, and we could just call our field phi sub L. But actually, I'll abbreviate even more and just call it little phi. But the action for a mode of angular momentum L, by a straightforward calculation, starting with the Schwarzschild metric and expanding phi in spherical coordinates, spherical harmonics, by the way, This calculation I'm showing you is explained in the lecture notes that you'll find online, and it will probably be easier to understand it there. Well, the details of the formulas, if you really want to follow them, you should look at the lecture notes and work through it more carefully. Then you'll be able to, by following me in real time. Anyway, if we take the action and just write it for mode of angular momentum L, we get what I've written here. And then it's convenient to introduce what's sometimes called the tortoise coordinate. Probably a terminology of John Wheeler, although I'm not sure. So explicitly, this is the definition of the tortoise coordinate, but it's convenient to know the relation between dr and dr star. It has the property, you see, we're interested in the region outside the horizon here. So r goes from 2gm to infinity. And while r is doing that, r star goes from minus infinity to infinity. R and r star are the same when r is near infinity, far from the black hole. But near the horizon, r is going to 2gm and r star is going to minus infinity. And as you'll see, it's very convenient to study the problem in terms of r star. Then if you let phi be sigma over r, you can write the effective action in terms of sigma, and you get dt dr star. The kinetic energy is what it would be in two-dimensional Minkowski space. But there's an effective potential. So we just get a Klein-Gordon equation for a massless field in an effective two-dimensional Minkowski space interacting with a time-independent potential. V effective depends on r or r star. And V effective is 1 minus 2gm over r times L plus 1 over r squared plus 2gm over r cubed. So it has the following properties. First of all, V effective is strictly positive for all r or r star. Secondly, V effective goes to 0 for r star goes to plus or minus infinity. So as I told you before, the wave propagates freely either near the horizon, which is r star equals minus infinity, or near spatial infinity, which is r star going to plus infinity. But in between, there's a potential barrier. And what we overlooked in the simple derivation that I gave yesterday and that we also reviewed in the first half of today's lecture is that potential barrier. So qualitatively, it looks something like this. In terms of, let's say, V as a function of r star. Okay, that's the eraser. Okay. So the potential is 0 near minus infinity. It goes back to 0 near plus infinity. So I'm plotting V as a function of r star. So near infinity or minus infinity, the particle is free. And in between, there's a barrier. So before we try to analyze this in detail, let's discuss qualitatively what we think might happen intuitively. So near the horizon, our previous discussion was correct. The wave was free. It just propagates freely. So intuitively, you might think that the black hole emits just as if there wasn't any potential. However, as you'll see, this maximum is near r equals 3gm, approximately. When you get to r equals 3gm, there's a potential barrier and the wave might be reflected back. Alternatively, it might be transmitted through the barrier. So an intuitive picture is that, an intuitive picture which we'll justify, but we'll start with it as an intuitive picture, that the previous answer for the radiation from the black hole should be reduced by a factor T of omega squared, where T of omega is the transmission amplitude. At frequency omega. And omega is the frequency measured by the observer at infinity, because in this representation, the potential is time independent. So omega is just a fixed constant. We've gotten rid of the redshifts and so on by this change of variables. So in the region near R star going to infinity where the distant observer lives, in this representation, there's just a time-independent potential, so a wave has a fixed frequency, which will ultimately be the frequency measured at infinity. It's not the frequency measured near the horizon, and the reason is that R star isn't a good coordinate near the horizon. The horizon isn't really infinitely far away, but in terms of R star, the horizon is infinitely far away. So R star is a bad coordinate near the horizon. It's a good coordinate for the observer at infinity. And the frequency in this representation is just the frequency the observer sees at infinity. So an intuitive picture is that what we got before should simply be reduced. What we got before for what the observer will measure at frequency omega was black body radiation at the Hawking temperature for that frequency, but we should now reduce it by T of omega squared, where T of omega is the transmission amplitude through the barrier. And we'll justify that, but, I want to tell you a few other things first. Any questions before I go on? Okay.
Any? Hear me? Yeah. Okay. Sorry. Any intuitive picture of what the effective potential is? It's like that.
Well, first of all, this is the formula for the effective potential. And what would you care about it? One is, where is it significantly non-zero? The answer is near R equals 3 GM. You can, there's no, for general L, there's not an elementary formula for the maximum, but for either L equals 0, a non-trivial fact is that even for L equals 0, there's a centrifugal barrier. So this potential is non-zero even if L is 0. This term goes away. This term, the Newtonian part goes away, but there's a general relativistic part of the barrier, even if L is 0. So the picture is qualitatively the same whether L is 0 or not. The maximum of this function is always near 3 GM, but the height depends on L. The height of the maximum is proportional to L squared, because for large L, the Newtonian term vanishes. Dominates. The Newtonian term dominates for large L. So you find that the maximum of potential as a function of L is roughly L squared times 1 over GM squared. And since our equation was phi double dot minus d squared, I called it sigma, right? Sigma. Our equation is that sigma double dot minus d squared sigma d r star squared plus v of r star times sigma equals 0. So this term will be minus omega squared. If and only if omega squared is bigger than V max of L, the potential is negligible. In other words, a wave whose frequency is high enough will, with probability very close to 1, just go over the barrier without anything happening to it. So our previous calculation gives the right answer for the radiation, for the high frequency part of the radiation. How high the frequency has to be depends on L. So if omega is bigger than, much bigger than L over GM. So, in other words, that's L over the Schwarzschild radius. So, if the frequency is large compared to 1 over the Schwarzschild radius, the previous derivation gave the right answer. But what we'll discover is that if the frequency is not so large, then the previous answer has to be reduced by a factor, which is the transmission probability over the barrier. So before giving a technical derivation of that fact, I just want to explain why it's a good answer to get. So suppose it's true that the black hole has temperature T Hawking. If the black hole has temperature equal to the Hawking temperature, then we expect it can be at equilibrium with thermal radiation at temperature T Hawking. So let's try to imagine what thermal equilibrium at temperature T Hawking would look like. It means there's radiation incident on the black hole from infinity. And radiation coming from infinity will meet this centrifugal barrier, so it might bounce back. Well, first let's discuss what would happen if there was no barrier, which we know is true for that magnetically charged black hole and a massless electron. If there was no barrier, then radiation coming from infinity would propagate freely and be absorbed by the black hole. But equilibrium would be maintained because in the simple calculation ignoring the barrier, the black hole also freely emits at the same temperature. Now let's imagine that there is a barrier. Well, the radiation coming from infinity might be reflected backwards. So the absorption by the black hole is reduced by the transmission probability over the barrier from right to left. T tilde is transmission from right to left, in other words, from infinity to the black hole. Well, since the barrier is reducing the absorption by the black hole, if it's possible to maintain equilibrium, it's got to reduce the emission from the black hole by the same probability, the same factor. So equilibrium requires that emission is reduced by the same factor. T tilde of omega squared, where T tilde is, remember, is the right to left transmission probability. However, emission, so the black hole is here and here's infinity, it's more natural to think of emission as being suppressed by the left to right transmission probability. So, naive or intuitive, you expect to get reduction by the left to right probability, by the transmission amplitude from left to right. But it's a simple fact about the one-dimensional Schrödinger equation that transmission amplitude from left to right equals the transmission amplitude from right to left. It's related to unitarity in one-dimensional scattering theory. And I'm going to take a moment to explain the proof, even though it actually is a standard result. So we're going to prove that the transmission amplitude from left to right through such a barrier equals the transmission amplitude from right to left. So, first of all, let's consider a solution of the Klein-Gordon equation with a definite frequency. So, of course, we can assume a time dependence at some given frequency and then look for a solution of the spatial equation. And the spatial equation is just a Schrödinger equation. And if the wave is incident from the left, we look for a solution with these boundary conditions. Well, the main idea is that as r star goes to plus infinity, we only want the transmitted wave because nothing was incident from the right. From the left, as r star goes to minus infinity, we start with a incident wave of unit amplitude, and then we have to solve for the reflected wave. So that's the general form of the solution of the scattering problem for a wave incident from the left. However, if we had a wave incident from the right, well, then we look for a different solution of the same equation. Now, in this case, we'd say that as r star goes to minus infinity, there should only be a transmitted wave. And I'll call the transmission amplitude from right to left T tilde. But as r star goes to plus infinity, there's a minus sign at the exponent because now the transmitted wave is going to the left. As r star goes to plus infinity, I have an incoming wave with a unit amplitude and a reflected wave with some unknown reflection coefficient. So that's those are the general form of the solution of the Schrodinger equations for waves incident from left to right. Now they obey the same equation, the same Schrodinger-like equation. So what's called the Wronskian is constant. In other words, in more detail, d by dr star of lambda dr star lambda tilde minus dr star lambda tilde is 0. So the Wronskian is constant, and then if you evaluate that as r star goes to plus infinity and compare it to r star equals minus infinity, you just get the result t equals t tilde. So to summarize this, the absorption by the black hole is reduced by, the absorption amplitude is reduced by t tilde. We're going to prove that the emission amplitude is reduced by t. But since they're equal, both absorption and emission are reduced by the same factors, and therefore equilibrium can be maintained. So the role of the barrier is going to be simply to reduce the emission from the black hole in the same way that it reduces the absorption. So any questions before we get into the detailed calculation? We're either all completely lost or else it's all completely clear. What's that? Oh, yes, okay.
So the question on the chat is, why are there only transmitted waves considered for one case of the lambdas?
Why or what?
Why are there only transmitted waves considered for one case of the lambdas?
I'm not sure I understand the question, but it might be why we only look at one partial wave at a time. It's because they're all decoupled. Rotational symmetry enables us to diagonalize the Klein-Gordon equation in a basis of partial waves. So if I understood the question, that's the answer. Any other questions? Okay. Okay. Now we're going to give a slightly tricky argument that is essentially in Hawking's original paper, although in my opinion it was improved a little bit later by Haag and Thiering. I'm going to draw the Penrose diagram again, schematically. So our observer is up here, remember? And what we've done so far was to introduce a hypersurface that I drew in blue yesterday, which we considered the signal to emerge from there. But now we're going to discuss more carefully what the observer is doing. And the observer's measurement is made somewhere up here. It means at a much later time than the signal was emitted, and also at a much bigger distance. Remember that the conformal mapping in the Penrose diagram obscures the fact that the observer is at a big distance. You'll have to trust me, or else perhaps you know from your previous study of Penrose diagrams that near this corner is the region where both R and T are large, far away and also late times. But now I'm going to draw a space-like hypersurface that passes through the observer. I'll call it S prime. What we're going to do is write down a formula for the operator that the observer is measuring, and then we'll interpret that operator in terms of initial data on the earlier surface S. So I'm going to assume that the observer measures W dagger W, where W is a linear function of the field that I called sigma. Well, we'll consider a rather general linear function. So any such W is, well, you see, sigma obeys a second-order wave equation. So it's determined in terms of its values and its time derivative on any initial value surface, such as S prime. So whatever the observer measures can be written as the integral over S prime of some function of sigma plus some other function multiplying sigma dot, where sigma dot means the derivative normal to the hypersurface. And H is the metric restricted to the hypersurface S prime. So whatever the observer measures will be something like that. However, it's convenient in doing this to assume that the surface S prime passes through the detector at the time when the observation is going to be made. And then we can assume that A and B are supported near the detector. So in that case, the operator we're describing has a transparent interpretation from the observer's point of view. We could do anything we want, but this particular case will be easier to analyze because it's more directly related to the experiment. So we take S prime to pass through the observer's world line of the far future, as I've drawn, and A and B are supported near the detector. Now, the observer, let's say, wants to measure the radiation flux as a function of frequency. For that purpose, we'd like to pick functions A and B that correspond to definite frequency, or approximately definite frequency. Of course, we can't make exactly definite frequency because that would give a plane wave that would fill all space and would be completely non-localized in time. The observer wants to measure the frequency dependence as a function of time that's only approximately defined. You have a certain time window in which you're measuring it that determines how precisely you can measure the frequency. But we pick A and B to be approximately proportional to e to the I omega r for some omega. Of course, we can't, r is the distance from the black hole, or r is simply the Schwarzschild coordinate, which is large where the observer is. We can't, of course, have exactly e to the I omega r because it would fill all space. But we can have a function that's rather well defined in omega, but still is localized in r, as much as the uncertainty relation allows. And then, if we pick the ratio of the coefficients of e to the I omega r and A and B correctly, we can make W an annihilation operator at frequency omega, and then W dagger W will be a number operator at frequency omega. So by measuring W dagger W, the observer can measure the photon flux at frequency omega at a given time. The time is simply the time where the hypersurface S prime passes through the observer's world line, and the frequency is whatever is picked in A and B. So this is an operator that would enable the observer to measure the frequency dependence of the outgoing radiation at a given time. So now we have to figure out what the observer will get. So to find out what the observer will get, we have to determine what W looks like on the earlier hypersurface, S, where we believe the signal originated near the black hole. Well, sorry. Okay. We can do whatever we want. A better way to say what I just said would be the following. The signal, whatever it is, can be considered to have originated along S. And figuring out what operator on S is equivalent to the operator W on S prime, W dagger W on S prime, will enable us to determine what the observer will measure. So we're going to reinterpret W as an equivalent observable on S. And the way we do that is we see, first of all, why is there such a representation? There is such a representation because sigma obeys a second-order wave equation. So as I said, any linear function of sigma can be written like this on the hypersurface S prime, but by the same logic, any such function can be represented in a similar way on the hypersurface S. So we're just going to figure out how to replace this formula by an equivalent formula on S. And as you'll see, that'll give us the answer we want. So to do that, we're going to reinterpret F. We're going to reinterpret the formula for W. We find a solution of the wave equation. So the wave equation is d mu F equals 0, except F is supposed to have the same angular momentum as sigma, same partial wave. With initial data such that F on S prime is B, and F dot on S prime is minus A. And then that enables me to write that W is the integral over S prime. So sigma mu is what's sometimes called the surface element of the surface S prime times F times d mu sigma. D mu with that double arrow over it means you take the derivative of on the right minus the derivative on the left. And with this choice of what F is, that is equal to what I had before. I've simply found F, well, what F must be along S prime, so that any linear function of sigma and sigma dot can be written like this in terms of F. Well, why did I do this? I did this because F and sigma obey the same wave equation. They obey the same Klein-Gordon equation. And since they obey the same Klein-Gordon equation, this thing F d mu sigma is a sort of conserved current. So the observable is the sort of the conserved charge for that conserved current evaluated on S prime. But if we simply write the same thing evaluated in S, that'll give us a formula for the same observable on S. So we immediately learned that W is the integral on S. Now sigma mu is the surface element on S. The same thing. So to interpret our observable as an operator on S, we simply need to know what F looks like on S. So, well, what do we have to do? We have the two initial value surfaces. There's S prime and there's S. We know F on S prime, and we have to find F on S. And F obeys the Klein-Gordon equation. So we have to integrate the Klein-Gordon equation backwards in time, starting from S prime to determine what happens on S. And on S prime, well, we constructed F so that W describes an outgoing wave at frequency omega. But now we're looking backwards in time. So looking backwards in time, F describes an incoming wave of frequency omega. So this incoming wave starts at very large R, where the observer lives. Then we send it in toward the black hole. We're trying to go backwards in time, but it will go in toward the black hole without going toward the future. We chose that because that's what the observer wanted to study. But now going toward the past, it's incoming. So we're sending a wave in from infinity where it's going to interact with the same potential barrier we discussed. It'll reach the potential barrier, and it might be reflected back toward infinity. So what we're going to learn is that W is a sum of two pieces. There'll be a piece proportion. I'm going to use T prime and R prime for transmission and reflection amplitudes backwards in time. So T prime is the transmission amplitude through the barrier for the backwards in time scattering problem. R prime, where you're coming in from the right. R prime is the reflection amplitude from the barrier in the backwards in time scattering problem. But what we're going to get is that W along the surface, W evaluated on the surface S. So we can evaluate W on any surface we want to. But for the present purposes, we want to evaluate W on the surface S. And what it will be is the following. There will be a reflected piece, which will be some operator near R star equals infinity. And there will be a transmitted piece, which will be some operator near the horizon. Well, if the transmission amplitude were 1 of the backwards problem, which would imply that by unitarity that we didn't quite prove that the reflected amplitude would be 0, then the transmission then that would say that W is just what it would be if there had been no barrier in the first place. And that's what we assumed yesterday and also in the earlier part today. So if this is the only important part of W, then we're just going to get the previous answer multiplied by T prime, except that when we make the operator W dagger W, which is the number operator that the observer is trying to measure, but then we'll get a factor of T prime of omega squared. So this will be T prime of omega squared times what we'd have times the naive story. And then there'll be other pieces. There's an R prime of omega squared. And this is going to look like a number operator near infinity. There also are cross terms. And now we need to take the expectation value of W dagger W in this hypersurface S, because that's equivalent to what the observer is trying to measure. All these stuff with contributions near infinity don't contribute. Well, one term is r prime squared times a number operator measured near infinity, but that's zero because there aren't any particles in the vacuum near infinity. Then the cross terms also vanish because the expectation value of the field is zero in the vacuum near infinity. So the only term that contributes is t prime squared times the naive answer. So we've learned that the effect of the barrier is to reduce the naive answer by a factor of t prime squared, where t prime absolute value squared. T prime is the right to left transmission amplitude backwards in time. Well, going backwards in time complex conjugates the amplitude. So T prime is the complex conjugate of the right to left transmission amplitude that we defined before. So it's the complex conjugate of the left to right transmission amplitude. So T prime squared, we justified the naive answer that what the observer measures is reduced from the naive answer by the left to right transmission probability. Well, this is roughly when we're supposed to end. I guess it's a good time, therefore, to stop. Conveniently, we've finished section 4 of my lecture notes, which I trust you're all faithfully reading. And for those of you who are behind in your reading, you have a little bit of time before the next lecture to start looking at section 5, where we will begin after lunch. But in any case, we could take a question or two now.
Questions?
So we are integrating in the black hole region as well, but those signals will never reach the observer.
I can't hear you, sorry.
So we are integrating over the black hole region as well?
By the black hole region, you mean the
Inside
interior?
the black hole.
Well, that's a very important question. Okay. We started with a function f on S prime, and then we integrated backwards in time to get the equivalent on S. The function on S prime had its support near the observer, and the observer was outside the horizon. And then integrating backwards in time by causality, the function f at the earlier time is entirely supported inside the light cone, which means it has no support behind the horizon. So therefore, the observer is not able to measure anything behind the horizon. If it were otherwise, we would have learned that what the observer measures had some information about what was behind the horizon. Very important question, which I skipped to save a little time in the explanation. You would have found it in the written lecture notes. Any other questions?
I was just wondering about the physical interpretation of the barrier being peaked at 3 GM.
It's approximately 3 GM, not precisely.
Oh, okay.
So you'll find precise numbers in the lecture notes, or they're easy to find. For either L equals 0 or L equals infinity, there's a simple formula for the maximum, and the maximum in each case is near 3 GM. What's important is only that, I would say, what's important is only that the potential is trivial near the horizon. And that's because near the horizon, the wave had a very large frequency and was effectively free. It's also trivial near infinity because there we're in the vacuum and the wave is free. But in between, there's a region where neither approximation is good. Yeah. There's something, yeah, and there's a potential barrier. I should say that the gray body factors are needed for the Hawking effect to make any sense. Suppose there were no gray body factors. Then we would conclude that the black hole radiates freely in every partial wave. And there are infinitely many partial waves, so we would have concluded that the luminosity was infinite. What happens instead is that since the maximum of the potential is of order L, well, order L squared, it follows that there's a cutoff at omega of order L over GM. So if omega is less than L over GM, the radiation is strongly suppressed. So in fact, in practice, that means since the temperature is 1 over GM, the radiation is strongly suppressed except in the first few partial waves. So I gave you an estimate before of the total luminosity, and that estimate was correct. But to justify it, you need to know about these gray body factors. So this is the right answer for the luminosity, but only because the radiation is cut off except for the first few partial waves. Any other questions? Some things you'll find explained a little bit more, in a slightly more organized fashion in the lecture notes. If there are no other questions, I think we should adjourn now and return at 2. If it is 2 that we're supposed to return. When is the next 2? Okay.